One of the most important and interesting sensor types in recent years is Lidar, mostly because of its central role in autonomous vehicle technology. The basic idea is remarkably simple. We can measure the distance to an object by bouncing light off of it and timing how long it takes for the light to return, assuming it does. More on that later. But like everything else in life and electronics, it gets a lot more complicated from there. Let's start with that basic idea. The first complication is that light moves very quickly, of course, about 3 times 10 to the 8th meters per second. In a vacuum, of course, about that in air. Fortunately, modern electronics has become so fast that we can do this with reasonable resolution. For example, let's say we have an object just 5 meters in front of a car. That's 10 meters round trip. Dividing by the speed of light, we find the delay will be just 33 nanoseconds. Not too long ago, that would have been hard to measure accurately, but now we can buy counters that run 1 gigahertz and faster for just a few dollars. For example, here's a device from ON Semiconductor that can count at 1.3 gigahertz. That allows us to count to 33 or higher in that short amount of time. Of course, the accuracy degrades as the distance gets shorter, but there are other methods that work well in these cases. For instance, triangulation methods take advantage of where the reflected spot falls on a linear scale if sent out at a slight angle. You can buy accurate laboratory equipment based on this principle. But let's concentrate on Lidar, especially as it applies to automotive technology. Most Lidar systems use laser emitters, and we all know what that looks like. A pencil-thin beam that extends to great distances with barely any divergence. Surprisingly, that's not true for most automotive Lidar systems. The beam is deliberately widened so that it covers a larger area. For instance, let's consider a Lidar sensor made by SICK. The beam divergence of their LMS1 is specified as 15 mrad, which is simply the beam width in millimeters divided by the distance to the target in meters. At 100 meters, the beam width will therefore be 1.5 meters. Hardly a pencil beam. Of course, it gets wider during the return trip as well. This limits the total energy received by any one detector, and thus the maximum detection range for a given output power level. So why is this done? In a word, coverage. Lidar systems generally spin the laser and detector to cover a wide area. The faster the spin, the more angular distance between the laser pulses. This can be reduced by using a faster pulse rate, but there are limits to that technique. A wide beam covers a larger area and allows for more angular distance between pulses without creating gaps. Designers can trade off these effects based on the capabilities of their system. Another important complication of Lidar systems is target reflectivity, which varies tremendously. Automobiles are made with a variety of materials that can reflect light brightly or hardly at all. For instance, chrome is a great reflector, while tires are one of the worst. Besides color, surface finish also plays a role. A smooth, shiny surface can reflect a lot of light, but perhaps in the wrong direction, like a mirror, so that little or no energy is returned to the detector. Matte or rough surfaces diffuse the light energy, which also reduces the return energy and thus limits range as well. All of these effects reduce the effectiveness of Lidar systems. But people seem to have few problems observing traffic or other hazards with their eyes. So let's compare the data obtained from a Lidar system with what you can see with your own eyes. It's easy to tell how far away objects are when they are fairly close to you because the same object is viewed from each eye at a slightly different angle. This is simply the triangulation method mentioned previously. But this gets a lot harder as the distance increases and the angles approach the same value. Other visual cues, such as the size of objects observed, add information, but in the end, it's a lot harder to measure the distance to objects when they are far away by eyesight. Lidar systems have no such limitations. As long as the target reflects enough energy to be detected, these systems can accurately measure great distances. This precision also means that LiDAR systems can detect speed accurately by taking repeated measurements and subtracting the difference. Compare that idea to observing a fast-moving car with your own eyes. If the car is moving perpendicular to the observer, its speed can be inferred from the background. But if it's moving directly toward the observer, arguably a more important case, the background hardly changes. The difference in angle seen by each eye is slight and changes slowly until the car gets very close. So LiDAR systems, using an entirely different technique, have a distinct advantage here. Light can be sensed by a variety of detectors, but the fastest are photodiodes. Recall that we need to measure some pretty short times for objects that are close to us, just tens of nanoseconds. This time is so short that detection can be limited by the speed of the response of the detector. Let's take a look at what is commercially available. Here's a screenshot from one of my favorite distributors, DigiKey. I limited the search to devices that can respond in a nanosecond or less, and see that there are 79 fitting the bill. They also vary by how much they respond, to what wavelengths, and so on. But the most interesting thing is the cost. Speed costs money, and all of the photodiodes in this fast category cost more than $12, even in large quantities. You can get entire microcontrollers these days for $1, so this is not cheap. Besides the cost of the photodiode itself, the electronics behind it are not trivial. Fortunately, high-speed photo detection is a well-developed art, and there are chips available that will do the heavy lifting. These are not cheap either. For instance, this ADA 4330 from Analog Devices has a very sensitive and fast front end, but for microprocessor applications, it also has an SPI interface. So what else can we say about LiDAR systems? There are additional difficulties involved in automotive applications. As we've mentioned before, the laser and its detector are typically spun by a motor so that a large area can be observed, often 360 degrees. A constant speed of rotation is not difficult to maintain, but only produces a single line. What about objects above and below this line of observation? It is possible to add a second degree of freedom to the scan and move the line up and down as well as around and around, but this adds mechanical complexity and requires a faster laser pulse rate. Velodyne and other manufacturers have chosen to instead add multiple laser beams and detectors that all rotate together. This can be more expensive, given the cost of the optics and the associated electronics, but provides better coverage for a given laser pulse rate since multiple lasers are used. By the way, the spinning laser and its electronics introduces the problem of getting power and data from the car to the rotating LiDAR system. There are two primary methods to do this: slip rings and inductive pickup. Slip rings are great for transmitting power, but produce electronic noise and wear out eventually. Not good for a continuously rotating system. Inductive pickup requires no mechanical contact and will last indefinitely, but adds significant electronic difficulty. Since an inductive pickup is similar to a transformer, the power part is not too hard, but moving high-speed data across that interface is another issue. There's a third way to conduct a signal between a stationary base and a rotating head. The original Velodyne HDL64 used this Mercatech mercury-based rotating coupler. It works just like a slip ring, but instead of brushes, there's liquid metal, so the noise level is much lower. Another difficulty with LiDAR systems mounted on automobiles involves pitching motions. As the vehicle accelerates, or especially during hard braking, the angle of the laser beams relative to the road will of course change. The system must provide enough coverage above and below the usual line of sight to accommodate such motion, and this means additional lasers and detectors that are not usable when the car is level. This adds cost to the system. For instance, this original Velodyne Lidar system specifies a 26.9 vertical field of view. It does this using multiple lasers. Alternatively, a servo system could be added to help keep the LiDAR unit level relative to the road, but this is neither simple nor inexpensive. One last note about detection. Given the beam width and size of potential targets, it is possible that multiple reflections will occur from one laser pulse as it encounters different objects at different distances. This poses a complex problem of interpretation to the software, which is already a tremendous challenge. Somehow, the algorithm must combine not only multiple reflections from multiple beams and decide what it's looking at. The fact that this can be done at all is a triumph of artificial intelligence and undoubtedly a subject of ongoing intense research. Data rate is a real issue with LiDAR systems, since in order to form a complete image, many laser pulses have to be sent and detected. Compare that to forming an image with a camera system, which has many detectors operating in parallel. Either way, a lot of data is developed quickly and must be handled at a fast enough data rate to react to changing traffic situations. A typical rate is 10 Hz. For a beam width of, say, 1.5 meters at a range of 100 meters, would have to produce and detect 21,000 pulses per revolution with no overlap and no gaps. For multiple beams operating in parallel to have vertical coverage, the data rate increases further. For example, a Velodyne Ultra Puck can produce about 1.2 million points per second. Moving that much data is well within the capability of modern electronics, but the problem doesn't end there. AI algorithms must interpret the data and decide what objects are in view, and how fast they are moving, and what action, if any, needs to be taken by the vehicle using the system. This is a very, very complex problem and will consume as much computing power as you can throw at it. One last note about an issue that has received scant press, and that is the issue of interference. We are used to seeing individual autonomous cars driving around, at least in the news. But what happens when there are many of them on the road, each sending out their own series of laser pulses? If the spot size was as small as a pencil beam, interference would occur, but not all the time. However, with realistic spot sizes that are much larger, we have the problem of one unit blinding another. This is not a trivial problem and will have to be addressed before large-scale adoption of LiDAR technology becomes commonplace.